So today we're wrapping up chapter 7. And so it's going to be kind of tying together these ideas that we've talked about so far in terms of, we've gone through like what is dimensional analysis, how do we use it to reduce down dimensional relationships to non-dimensional ones, and then the question is what do we do with those? We saw a little hint of this in the first example where we said let's look at look at figuring out the pressure drop in a water delivery pipeline using our airflow lab in the Siemens Center. But we're going to kind of formalize that today through this discussion of what we call, here we go, modeling and similitude. So our objectives here, we want to be able to use model scale studies on problems that involve 4 or more pi terms. Okay, so those where it starts to become it's not very economical to try to do this general sort of correlation that we talked about last time. Apply concepts of similitude / similarity. Okay, these terms are equivalent, just depends on what textbook you're using. To select model test conditions. And then finally, once we have a measurement in model scale, we want to be able to scale model testing up to full scale. And so through these 3 steps, right, we're kind of looping back and going full circle on that pipe pressure drop problem. We're done with pressure drop in pipe, so we're not going to do any more of that. But we're going to sort of understand what allowed us to select those conditions where we were able to model the pressure drop through a water-filled pipeline using airflow through a 2-inch diameter pipe. So quick little recap here, okay? Just to kind of get us resituated. We closed out last time talking about if we applied dimensional analysis to the Navier-Stokes equations themselves, then we ended up with this collection of dimensionless groups. Okay? This collection of dimensionless groups is really, they're not, you don't have to end up with these anytime you're doing a model scaling study, but they're useful because, as I mentioned before, they represent the sort of relative balances between different types of forces. So inertial forces relative to viscous forces, meaning that if the Reynolds number is really large, that means that the inertia of the fluid is much more dominant in its dynamics, okay, than the shear stresses that are acting within the fluid. Likewise, the Screw-Hall number suggests that the time unsteadiness of a fluid relative to the convective inertial force it bears some resemblance or has some relationship. So dimensional analysis, as we applied it so far, has basically been kind of followed the pattern of, we say we've got some dimensional relationship, right? U1 is some unknown function of U2, U3, UK, right? And these are dimensional variables. If these variables contain R reference dimensions, then the Buckingham pi theorem, the BPT, allows us to know that we can reduce this down to a new relationship between dimensionless pi terms. 2, 3, pi k minus r. Okay, where we can basically reduce the dimensionality of the problem down by by this number r. And then last time we said, okay, so once you get to this point where you figure out what the value of k minus r is, in other words, once you know how many pi terms are going to be present in your new dimensionless relationship, you can start to tackle the question of like, how do you represent them, how do you use them? And we said really, we went through 3 cases only. We said if k minus r is equal to 1, okay, then we have pi 1 is equal to a constant. So you figure out what pi 1 is, or you come up with an expression for this. You do one experiment, you figure out what this constant is, and you've got a universal description. Okay. K minus r is equal to 2. Then we've got pi 1 is some function, pi 2, and we represent this by collecting data. Of pi 2 versus pi 1 and fitting a curve through that data that approximates this function phi. So we did this example for a case with a pressure drop through a pipe. And then if k minus r is equal to 3, we said then we've got either a 3-dimensional surface or a family of curves. 1, 2, phi of pi 2 and pi 3. And so if you take slices through this surface, for example, pi 2 versus pi 1, you'll end up with pi 3 is equal to C1, pi 3 equal to C2, pi 3 equal to C3. So you can have one of these correlated curves fitted by changing pi 3 to constant values and then rerunning this experiment. But you can see that the number of experiments you have to do in order to have some curve fit is really quickly going to pile up. And so when you have more than 3 pi terms, this really quickly breaks down. And it's no longer economical to try to come up with a general correlation, okay, or some approximation to this function phi. And so we're positing here, okay, our premise is that if you've got 4 or more pi terms, 4 plus pi terms, experimental correlation is not generally economical. And so in cases like this, it quickly becomes it becomes a better use of our time and effort to look at specific configurations of the problem we're interested in. So let's motivate this with an example. Quick, let's consider a case where we've got, does that can work? Maybe, there we go. Let's consider a case where we've got this, this office building. This office building that is topped with a smokestack for some nefarious purpose. Burning papers, one the SEC shows up or something. So the question is, like, what maybe the engineers want to know what the drag on this building is. Okay, those of you that are civil engineers would find this particular question, because you got to design the foundation and the structure for the building to support the wind load on it. And so we've got to say, all right, what variables are going to affect the drag? Okay, so if we've got wind blowing in here in this direction, okay, we can expect that there's going to be some drag force acting on the building as a result of that. So what functions might the drag or what variables might the drag be a function of? Well, there's a whole host of them, right? You can name your choice. We've got the we'll say we've got the width or the breadth of the building here. Okay. Say the width of the building in this direction. Say the height of the building. Okay. Say the height of this this chimney. The chimney diameter. Maybe this building has windows, okay, that are HW high by W wide. Okay, so we're on H, B, W, D, L, height of the windows, the width of the windows, right? The number of windows that are present. Obviously, the wind speed is going to come into play. Okay, velocity, as well as, right, the density and the viscosity of the wind or the air. Rho, mu. And we could just keep going, right? Maybe we're interested in, it depends on how far you want to zoom in on the problem, right? The exterior surface of the building, whether it's concrete or riveted steel or glass plate, is going to have an influence on the wind drag, right? Where doors are distributed might have an influence. There's an almost endless list of potential variables. If we cut it off here, right? We've got how many dimensionals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we've got 12 dimensional variables. Obviously, trying to vary each one of these systematically is going to lead to just a stupid number of experiments. Right? So we could say, all right, dimensional analysis allows us to reduce down the size of this relationship. Well, not by as much as we might hope, right? Because we've got how many reference dimensions? Usually only 3, sometimes 4 if temperature is important, but in this case it's not. Right? So in this case, if we apply our dimensional analysis, and let's select, say that our repeating variables in this case are rho, v, and b, then what we'll end up with is d over rho v squared. B squared is equal to a function of h over b, w over b, d over b, l over b, hw over b, ww over b. The number of windows, and then rho v b over mu. Okay. So you can see in this case, these are the pi terms, say pi 1, 2, 3, 4, 5, 6, 7, 8, 9, that come out of applying this method of repeating variables with these repeating variables selected. So each one of these is now dimensionless. Right? These ones we can see that pretty easily because each one of these is simply a length dimension divided by another length dimension. You can send ratio. Here we've got force over rho v squared times b squared, which you can take my word for it right now that that's dimensionless. And then this is the Reynolds number that we've been talking about if we consider that b is our length scale of interest. But the more pressing concern here is that we've still got 9 pi terms. Right? So if we wanted to create a general empirical correlation out of this, in other words, a database that has every combination of every one of these variables, then we have to vary all 8 of these independent pi terms. If we want to do it for 10 different values of each one, then all of a sudden we're running 10 to the 8th experiments. We're not going to run 10 million experiments or 100 million experiments. Okay, that's completely inconceivable. And so it really quickly becomes more practical, rather than trying to come up with a general correlation, the way we were doing with curve fits in the previous lecture. It really becomes more practical to go to the engineers and say, all right, what is your design intent for this building, and how can we scale that down to a model test so that we're only testing one condition, but making sure that that condition matches the conditions of interest for the full scale. Okay. So in this new frame, let's set up a little bit of terminology. For model testing, the prototype is what we refer to, or is how we refer to the full scale object or system. And then obviously our model is a reduced or sometimes enlarged version of that object. And so the premise is we're saying, okay, we've got this dimensionless relationship that pi1, we'll say pi1 of the prototype is equal to, right, phi of pi2 of the prototype, pi3 the prototype, pi, et cetera, all the way up to pi, in this case, 8, right? Or sorry, 9 for the prototype. This would be our building. So we go to our engineers, so the folks that are looking at designing this building, and we'd say, okay, what are your conditions of interest? Okay, what is it? Maybe the worst case wind speed you expect this to operate in, or the average wind speed you expect this building to stand in. And from those conditions they give us, we compute everything on the right-hand side. The question is, what is this pi term on the left side? That's the one where we actually need a value in order to get the drag, okay, because we get the drag coefficient. So if we make a model of the system, we assume, right, that this function applies still as phi, this unknown function, because this function doesn't care whether the pi terms on the right and on the left are at model scale and full scale. They just see the numbers. So we assume that then pi1 of the model scale has the same functional relationship phi, okay, but now depending on the pi terms at model scale. So it should hold then that if each one of these pi terms at model scale is made to match that at full scale, okay, in other words, if we're plugging all the same numbers into this function phi, then we should get the same output from that function phi. So if pi2m is equal to pi2 at the prototype scale, right, pi3m is equal to pi3 prototype, etc., then pi1 at model scale will equal pi1 at the prototype scale. So the sort of the outline of how we apply this then is we've got a prototype system. We don't know this, but we do know these because these are dictated by our conditions of interest. So we come up with a model that's easier to assess this. We say, all right, we've got everything on the right-hand side, so we adjust our model's size, the test conditions, etc., until all the terms on this side match. Then we actually perform the test. We come up with this. We say, hey, we matched all of the right-hand side, so this pi1m is simply equal to this, and we've indirectly gotten the result of interest at prototype scale through our model test. So this matching of pi terms between different scales is what we call similarity or similitude. And so we're going to take a brief digression into the three types of the three types of similarity that exist or that must be maintained for model scaling to work. So similitude basically it means that, I'm trying to think here the best way to explain it. If you're testing something at model scale that you want to observe at full scale, it makes sense, right? It's intuitive that you want the flow to look the same, right? And for all the physics to be maintained. And so similitude here is simply a way of saying that you are maintaining a similarity, okay? They're not at the same scale, but they have the similar flow behaviors at model scale that you would have at full scale. And so similarity or similitude, as I said, comes in three flavors. And model scaling, right, to be a faithful representation of a full-scale system. Must satisfy all three of these similitude requirements. Those are geometric similarity, dynamic similarity, and kinematic similarity. Okay, and if all of these similarity conditions are satisfied, then you can say that similitude of the problem has been achieved. So taking a look at just the names of these, right? There's something to be gleaned from the name. The geometric, obviously, the shape of things. Okay? Dynamics, we've discussed this distinction between dynamics and kinematics before, but dynamics has to do with the forces that are acting on something. And kinematics has to do with the way that things move. And so we're basically saying that for a problem to be accurately scaled, the shape has to be similar. Okay? The forces acting on our system have to be similar. And the way that movement occurs in our system also has to be similar. So if those three things occur, there's no other way that the physics can differ between our model scale and our full scale. So geometric similarity is defined as perfect geometric scaling of all physical dimensions by a single geometric scale factor, which we'll define as lambda L, okay, which is the length, of some length of our model relative to the same length on the prototype. So what this means then is if we've got a box, okay, for our prototype that is H W by L, okay, P, P, and P. And we've got a scaled down version of this box, WM, LM, HM. This geometric similarity requirement is that HM over HP is equal to WM over WP is equal to LM over LP is equal to whatever the scale factor is. Okay, it's nothing different than simply saying you're going to shrink down your thing and maintain all of the relative dimensions the same way. You can't have angles out of whack, etc. This is actually a bit of a snake in the grass, so to speak, because when you require dimensional or geometric similarity, every geometric feature has to be maintained. Okay, that means bolt heads, roughness, things like that. You have to be able to scale down if you want true geometric similarity. In practice, though, so say geometric requires all geometric features to be scaled but small features such as roughness or, like I said, fasteners, roughness, welds, fasteners, etc., are often neglected when creating a small scale model. There's sort of a truism in engineering that it's really expensive to make things big and it's really expensive to make things small. And if you're taking a complicated system, right, you're taking a skyscraper and you're trying to scale it down and you want to maintain perfect geometric similarity, then you basically have to get in there with nanofabrication to achieve the really fine dimensional features, the really fine geometric features. And it's going to quickly become completely impractical to do that. And so you sort of have to pick which ones are important. So the gross dimensions of building, great. So that's geometric similarity. Dynamic similarity is the second of these requirements. Dynamic similarity. And this says that ratios of forces of different types must be maintained at model scale. And so this is where we come back to that list of classic pi terms that I had up here in the first recap page. Let me pull that up quickly. Right? Because each of these terms, as I said before, can be interpreted as a ratio of forces of different types. And so what this is saying is that if you've got, right, at full scale, if the inertial forces over viscous forces have some relative importance, and that importance needs to be maintained at your model scale. And the way we do that is by making sure that our Reynolds number is equivalent at the two scales. So if at prototype scale we've got some Reynolds number, which represents the ratio of inertia to viscous forces, this needs to be maintained at our model scale. Likewise, if we've got something involving a free surface with a Froude number, which is inertia over gravitation, this needs to be maintained at model scale as well. So if geometric similarity and dynamic similarity are achieved, okay, then the result will implicitly be the third type of similarity, which is kinematic. So kinematic similarity says that streamlines, angles, and ratios of velocities or accelerations
must be maintained at model scale. In other words, it's saying that the flow should look the same. So if you've got flow around some blunt object, here's our prototype, and you've got flow occurring around this, where you've got maybe let's say recirculating flow. Then when we shrink this down to model scale, okay, by making sure that it's geometrically similar and that the relative forces acting on the fluids are similar, then we'll ensure that the resulting flow field will look the same at model scale as it does at prototype scale. And so this is all a really formal way of saying, right, this idea of this is what we want. Okay, this is our objective, and the way we get to that is by ensuring the geometric and the dynamic similarity. Now, if we step back really quickly to our set of dimensionless variables that we posited in this relationship, for each of these geometry-only variables, okay, the h over b, w over b, d over b, l over b, right? If we ensure geometric similarity when we pick a model scale, in other words, if we don't distort the model somehow, then each one of those ratios is automatically going to be equal to model scale to the value of prototype scale, right? So geometric similarity is basically saying that all of our geometry-based terms in our dimensionless relationship have to be maintained. We've only got one other variable here, which is the Reynolds number, which is that balance between inertial and viscous forces. So by satisfying the Reynolds number, then we've guaranteed our dynamic similarity. And so we're achieving similitude, okay, by matching pi terms at model scale and at full scale. That's the short of it. So similitude is achieved by matching all pi terms between model and prototype scale, or model and full scale. Which is one reason that you'll see pi terms sometimes referred to as similarity parameters. Okay. So we're going to quickly go through kind of the steps that are involved in dimensional analysis and model scaling and expanding those results to full scale. Once I'll throw it out on a slide, and then we'll do an example, and that'll close us out of Chapter 7. So briefly, here we go. So I've proposed that this sort of 6-step process can be used for model testing, right? Step 1 is perform a dimensional analysis on a problem of interest. That involves some steps of its own, as we've seen, right? Apply the Buckingham Pi theorem, use your method of repeating variables, so on and so forth. Step 2 is compute the values of all similarity parameters on the right-hand side. In other words, in order to do model scaling, everything that's on the right-hand side at your prototype scale, you've got to have a value to assign to that. So, for example, in our problem with the drag on the building, we've got d over rho v squared b squared is equal to some function of like h over b dot dot dot,
then to rho v b over mu. Okay. So we're saying that the left-hand side is our condition of interest, and in order to get any further in this problem, we need a numerical value for each term on the right-hand side. Okay, step 3 is figure out how big your model can be while ensuring geometric similarity. Okay. And so in this step, by ensuring geometric similarity, all of the pi terms that involve only geometric descriptors, okay, ratios of lengths, angles, what have you, should automatically be satisfied. Number 4 is adjust your model test conditions, or the fluids you're testing in, or other parameters of your experiment, to achieve equality in all of the remaining pi terms on the right-hand side of your model scale. And by doing that, you're hitting that dynamic similarity requirement. Okay. Then you measure the result of interest model scale and calculate the pi term of interest on the left-hand side. You say, if I match all pi terms by achieving similitude between my model scale and my prototype scale, then that dimensionless result of interest can be plugged directly in at the prototype scale. Okay. And so we've got, that's step 6 here then, right? Saying that we're assuming that similarity allows us to take our dimensionless result from our experiment and say that's equal to the dimensionless result at prototype scale. And then we can re-dimensionalize our result of interest because whatever else is in the term, okay, like rho v squared, b squared, those are terms that are prescribed by the engineers. Okay, those are part of the test conditions. And so those are already known. So let's go ahead and revisit this, this wind force on a building. I'm going to grab my drawing of the building again. And let's assume that the engineers behind this thing have decided that the dimensions will be as such. H is 150 meters. The smokestack is 30 meters with a 0.5 meter diameter. And the base is going to be a square, 20 meters by 20 meters. They're interested in knowing what the drag force is when the wind is blowing 20 meters per second. Okay, and we're going to assume that the density of the air here is kind of the density and viscosity at standard temperature and pressure. 1.79 fifth Newton second per meter squared. And then we're going to write the distribution and size of windows, etc., is going to be whatever it is. Okay, those would be numbers that we could get from them upon request. And so we've already established at this point, right? We've kind of gone through step 1, which is perform our dimensional analysis. And that gets us, right, that drag over rho v squared to b squared is equal to h over b, w over b, l over b, d over b. height and width of windows over B, the number of windows, and then rho V B over mu. Okay. Step 2 is compute values for the pi terms. So we've got, right, the h over b is equal to 7.5, w over b is equal to 1, right? The other values, etc., we could compute, the different length ratios, but the one that we're really interested in, okay, is going to be the rho v b over mu, okay, which we'll call the Reynolds scale at the prototype, or the Reynolds number at the prototype scale. And for this value, if we plug in this density, this viscosity, this wind speed, 20 meters per second, and the 20 meter value for B, we're going to get a value of 2.75 times 10 to the 7th. All right, so the engineers that are designing this thing say, okay, we want to know what the drag is for these conditions, but all we have access to is some sort of recirculating flow channel. It's like a wind tunnel, but maybe we can put other fluids in it if we want to. So we have access to a flow channel with a pressure that's controllable up to 10 atmospheres or 10 bar, okay? So it can be pressurized, whatever fluid is in there, and can accommodate a 3.6 meter tall model, okay? So this is sort of our limiting factor in how large our model can be. And so this is going to now affect step 3, which is scale the geometry of our model to maintain geometric similarity. So step number 3, scale model geometry. So if all we can achieve, if we're limited to if the total height of this thing, okay, the building plus the spire on top is 180 meters, okay, that 150 meter building plus the 30 meter smokestack, and the tallest model we can get in there is 3.6 meters. We'll go ahead and say, all right, we'll go with, we don't go big or go home, we'll go with like 3.6 meter model, which is pretty large. It's still a 10-foot model building. So that suggests then that our scale factor, gamma L, which would be, right, like height of the model over the height of the building, would be, right, basically the 3.6 over 180, which will work out to be 1 over 50. So we could write out a kind of a table of dimensions here that says H, right, B, W, L, D. Okay, the prototype, this is 150 meters, B is 20 meters, 20 meters, oops, 30 meters, and the diameter of that smokestack is 0.5 meters. At model scale, then, this works out to 3 meters, right? 0.4 meters, 0.4 meters, 0.6 meters, and then a smokestack diameter of 0.1 meter or 1 centimeter. Okay, so everything gets scaled down by the same 1 by 50 scale factor. And if we do that, right? Now if we look at all of our pi terms, now we already kind of ranked this home, but if we look at any of our pi terms that involve length over b, h over b, okay, then our ratios of dimensions in model scale and prototype scale are going to be equivalent. So we're good on geometric similarity. Okay. Step 4 is achieve dynamic similarity. And this is where things get a little bit more interesting. Because basically, our geometric similarity is taking care of all but one pi term. Okay, the only pi term left on the right-hand side is our rho VB over mu is equal to, right, 2.75 times 10 to the 7th. So the way we achieve this then, okay, the way we match this value is we're saying, all right, if this is our prototype scale, so rho p, vp, bp, and mu p has to be equal to rho model scale times v model scale times b model scale over the density at model scale. So generally the most prescient question that people ask when they're running experiments like this is how fast does the flow have to be going? And it's one of the real make or break decisions. And so we could solve for the model scale velocity that we have to test at, right? Vm is going to be equal to, right, rho p over rho m times bp over bm times mu m over mu p times vp. This is just solving this up here, okay, for our model scale of velocity. So we could consider a couple of different fluids that we might test in. We are, how does that happen? You know, for example, we can run this thing in, I've got a table made up here that I had 4 different ideas for fluids that you could run this in. Okay. If we filled our wind tunnel with air, okay, at atmospheric conditions, in other words, the same air at standard temperature and pressure, air pressurized at 10 bar, okay, so the density is escalated by 10 times, and the viscosity stays unchanged, at least according to the ideal gas law. If we filled it with water, and then finally if we just got real reckless and filled the entire thing with gasoline. So it turns out that air, standard temperature and pressure, right, here's our scaling law. We end up with these both going to 1, right, 1, and this being 50. And so it's saying that model scale has to be 50 times the prototype scale. 1,000 meters per second. We're in a hypersonic flow at that point. Totally unrealistic. If we pressurize the air to 10 bar, it goes to 1 over 10. This goes to 50. This remains at 1. Now we're at 100 meters per second. Much more realistic. Okay, this is something you can actually achieve in a modern wind tunnel. If we go with water, example, we end up with 77 meters per second. And finally, in gasoline, we would only need to go 31.3 meters per second. Okay. In any of these conditions, okay, if you were to compute the Reynolds number down here, plugging in Vm with our mu m, our rho m, and then that
dimension b of the model, we would, in each case, get our 2.75 times 10 to the 7th power. Okay, that's what we're doing here. We're solving for the velocity needed to achieve that Reynolds number similarity. I think that we're going to have to finish up with the last few steps in this actually on Monday.